You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technical specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. The flyback converter with current mode control is widely used in isolated applications below 150 watts, in which an optocoupler transmits the output voltage feedback signal across the isolation barrier for regulation. This means that the optocoupler is part of the feedback loop, and its characteristics need to be considered when designing the compensator to ensure stability as well as good transient performance of the converter. Today's podcast is presented by Elazar Falco, Worth Electronics application engineer. Elazar recently hosted a webinar in which he described how to design an optocoupler-based Type 2 compensator to stabilize a current mode flyback converter in CCM. He also covered how to estimate and assess the impact of optocoupler CTR variations and pole frequency, and finished off on how to achieve a fast transient response despite the optocoupler pole limit. Sit back, relax, and enjoy Elazar Falco's presentation, Feedback Loop Compensation of a Current Mode Flyback Converter with Optocouplers.
Thank you very much, Amelia, for the introduction, and hello to everyone. Also very welcome from my side to this webinar, where we will learn how to compensate a current mode flyback converter with special attention to the optocoupler in the system. My name is Elazar Falco. I'm application engineer for switching power supplies at Worth Electronics. In today's webinar, we will start by studying the characteristics of the plant, also known as control to output transfer function of the flyback converter with peak current mode control, and for operation in both continuous conduction mode, CCM, and discontinuous conduction mode, DCM. Based on the plant characteristics, we will set the requirements for the compensator and select a compensator type. For the design shown in this webinar, we will select an optocoupler-based Type 2 compensator, and we will learn its principle of operation and go through the circuit design steps. As required for the compensator DC bias design, we will learn how to estimate the variation of the optocoupler current transfer ratio, CTR, for our specification. And we will also learn how to overcome the limitation of the optocoupler frequency limit with two different compensator design examples. We will look into the resulting characteristic of the open loop transfer function and the load transient response for this design. And we will see the effect that the optocoupler CTR and pole frequency variations might have on the system. That will be followed by experimental results in a prototype, and we will finish with the usual questions and answers section. Note that in order to be able to follow the content of this webinar, you should already come with basic knowledge of electronic control systems and feedback loop compensation of switching power supplies in general, since we will not be covering the basics here. So let's start with the plant transfer function of the current mode flyback converter. Here we can see the flyback converter power stage with an optocoupler-based compensator and a peak current mode duty cycle generator, all together forming a closed loop system to regulate the output voltage of the converter. We will not go here into the details, but we'll focus on the Laplace transfer functions and input and output variables for each block. The plant control to output transfer function, HS, is formed by the duty cycle generator block with transfer function GS and the power stage with transfer function PS. The duty cycle generator receives as the input the compensator voltage, VCO, as well as the voltage across the sense resistor, which is simply an image of the transformer magnetizing current. It then outputs the duty cycle, which is then the input to the power stage, with the converter output voltage being the output of the power stage block. Then we have the compensator with transfer function CS, which receives as the input the converter output voltage and outputs a voltage to the peak current mode duty cycle generator block. The system can be represented by the following unity gain closed loop diagram, and the open loop transfer function is simply the product of the compensator and the plant transfer functions. And here we can see the structure of the plant transfer function for our peak current mode flyback converter and continuous conduction mode operation. A typical body plot example for this transfer function, showing the magnitude and the phase versus frequency, is also shown here. The different components of these transfer functions that we have are the following. First, we have the so-called DC gain, which is simply the magnitude in the lower frequency range, way before the dominant pole frequency. Then we have a dominant pole, which dominates the response in the lower frequency range. The pole causes the magnitude to roll off at -20 dB per decade, and it causes phase lag as usual, starting about 1 decade before the pole frequency and reaching up to -90 degree 1 decade after the pole frequency. But in this case, we see it does not quite reach -90 degree because we also have the so-called ESR0, which the ESR0 frequency is inversely proportional to the converter output capacitance and its ESR value. And from that, it comes its name. In the case of this plot, high ESR capacitors, like electrolytic type, were considered in the design, causing the ESR0 to appear here in the lower frequency range. However, if low ESR capacitors like MLCCs were used instead, the ESR0 will happen at much higher frequency in the megahertz range and will not appear here in the response. In this case, we can see how the zero pushes the phase curve up, and it causes the magnitude curve to flatten as it counteracts the dominant pole action. Then we have the right half plane zero, which acts like a zero in the magnitude, causing it to increase, but it behaves like a pole in the phase curve, causing it to decrease, so adding more phase lag as shown here in the curve. And finally, we have a resonant double pole at half of the switching frequency, which represents the subharmonic oscillation instability which happens in peak current mode control systems as the duty cycle approaches or exceeds 50%. This resonant double pole causes a peaking in the magnitude, as we can see here, and the amplitude of this peaking is directly proportional to the duty cycle at which the converter operates. We also see how the double pole causes a dramatic phase lag of -180 degrees. As we will focus on the compensator in this webinar, we will not go into all the details for the plant transfer function and all the formulae for the different factors. For this, you can refer to the book Transfer Functions of Switching Converters from Christophe Basso, which was also used as a reference in this case to plot the frequency response of this transfer function and also those who come in the next slides. Now that we know the typical characteristic of the plant transfer function, let us study it for the specification used in this design. Here we will consider a typical class 4 power over Ethernet application where the flyback converter is used in the power device. So we have a wide input voltage range from 36 volt to 57 volt with 12 volt output voltage and a total maximum output power of 30 watts. The switching frequency is 300 kilohertz, and the transformer used is from the POEH series from Burst Electronic together with a controller NCP12700 from onsemi. The output capacitance of the converter was implemented by a capacitor bank, as shown here. And this is the magnitude and phase response of the control to output transfer function for minimum, nominal, and maximum input voltage as plotted in MATLAB. We can see that the characteristic is very similar to that of the previous slide. However, a closer look to the phase curve will reveal that we don't really have an ESR0 here. Well, in fact, we do have one, but since we are using MLCC capacitors, it happens at about 4 to 5 megahertz, which is out of the frequency range of this plot. We can observe how the amplitude of the peaking is dependent on the input voltage, and especially for the minimum input voltage of 36 volt, which corresponds to the maximum duty cycle in this design, around 50%, the peaking is very high and it needs to be damped with some ramp compensation. If it is not damped, then we might have several problems. One of them is a very low gain margin of the open loop transfer function. And another one, which might be even worse, is that the open loop transfer function might cross over the 0 dB line more than once, and that will make stability analysis more complicated in this case. The controller used in this design have an internally adjustable compensation ramp whose value is adapted based on the switching frequency and the duty cycle. And here we can see the table from the data sheet. We see that for a switching frequency of 330 kilohertz, the ramp compensation provided is between 81 and 33 kilovolt per second. In our converter, we will have a switching frequency of 300 kilohertz, and we will expect a minimum ramp of around 30 kilovolt per second. With this, we can see here in the plots with the minimum ramp compensation of 30 kilovolt per second, how the peaking is well damped even at this minimum ramp. So we should not be worried much about it. Eventually, as the load current reduces, the converter will enter this continuous conduction mode operation, DCM. In the case of this design, that will be for a load current below 1.2 amp. And it is important to note that the control to output transfer function will be different depending on whether the converter operates in continuous conduction mode CCM or in discontinuous conduction mode DCM. Here we can see the body plots of the plant for DCM operation and an output current of the converter of 0.8 amps. It can be observed how it is mainly a first order system with a dominant pole whose frequency is depending on the output current of the converter. The system still has a right half plane 0, but it happens at a higher frequency than in continuous conduction mode, and in some cases, it is not even modeled. In this continuous conduction mode operation, there is no subharmonic oscillation instability, so therefore no double pole and no peaking of the magnitude curve in the system. So with this, we can see how continuous conduction mode presents more challenges for compensation, and this is due mainly to the right half plane 0 influence at a lower frequency. Also considering, on top of that, the peaking in the magnitude caused by the double pole resonance. For this reason, the compensator is typically designed for CCM at minimum input voltage and at the highest output current, so full load, and then any adjustments can be made if necessary in order to ensure stability and good transient performance over the full range of operating conditions, also for DCM. Alternative to the analytical approach, the body plots of the control to output transfer function can also be obtained by means of a SPICE simulation, as shown here for a current mode flyback converter in LT-SPICE. For this, we will need to use an average PWM switch model, which is the yellow box here. What it does is simply averages the voltage and currents of the converter switching network, and with that removing all the switching transitions, and with a time continuous system, we can run an AC simulation in LT-SPICE. Just talking a bit about this simulation setup, we have the typical resistor divider to set the output voltage. Then we have an error amplifier implemented by a voltage-controlled voltage source with a reference. And we see this inductance in series, very high inductance value, that makes the system to be closed loop for DC and open loop for AC. And that is used to set the DC operating point of the converter. In this case, will be minimum input voltage and full load. We see how the AC signal is injected here, and that is when we design the converter at the end, that will correspond to the output voltage of the compensator. So this will be the node output of the compensator, which goes to the peak current mode duty cycle generator input. So then we run the simulation and we obtain the body plots of the control to output transfer function by just clicking on the output voltage node here. The solid line represents the magnitude with reference to the left axis, and the dotted line represents the phase with reference to the right axis here. For more information about how to put together this simulation, you can consult the book Switch Mode Power Supplies, SPICE Simulations, and Practical Designs, again from Christopher Basso, which I used to put together this simulation. You might have to do some small adjustments to the SPICE netlists provided, like for example, also modeling the transformer with two arbitrary sources depending on each other, like here, because for the model, it needs to operate in DC, but also in AC. So DC to set the operating point, the DC operating point, and then also for AC. But anyway, small modifications which are not difficult to do. The simulation results in LT-SPICE can be then exported to a text file and then imported into MATLAB, and so they can be compared to the analytical results as it was made here. We can see an excellent match of these two approaches in this case. So these two options, analytical or SPICE simulation, or both, can be used in order to study the control to output characteristic of the converter, which is a necessary step which we will need to set the requirements of the compensator. And that is what we will do next. The first step is to select the target crossover frequency of the open loop transfer function. Here we must consider that the higher the crossover frequency, the faster the reaction time of the closed loop system will be. However, there is a maximum recommended limit, which is 1/5 of the switching frequency or 1/3 to 1/5 of the minimum right half plane zero frequency, whichever is lower. The minimum right half plane zero frequency is calculated with the expression shown here, which corresponds to minimum input voltage and full load operation. And we can see here, because at the minimum input voltage, we have the maximum duty cycle, and at the maximum converter output current, we have the minimum converter load resistance. Then we need to set the phase margin. And for that, we must consider the transient performance of the converter. A simulation of the converter in LT-SPICE with an average PWM switch model shows that a phase margin above 45 degrees provides a response with no ringing. We can also observe how the settling time for 45-degree phase margin and 60-degree phase margin is mostly the same in this case. And we can also see how too high a phase margin approaching 80 degrees also increases the settling time. So with this in mind, we can target for a phase margin of 70 or 60 degrees. So from 60 to 70 degrees, and then with a minimum worst case phase margin of 45 degrees as a good design approach. Regarding the gain margin, it should be higher than 6 dB. In this design, the switching frequency is 300 kHz, and the resulting minimum right half plane zero frequency is around 70 kHz. The right half plane zero is clearly the limiting factor in this case, and the crossover frequency will need to be set lower than 14 kHz. For this design, we will select a slightly lower crossover frequency of 10 kHz. Now we need to know the planned magnitude and phase at the target crossover frequency. Note again that this body plot is for minimum input voltage and full load, and the magnitude is minus 12.3 dB and the phase minus 96.4 degree at 10 kHz. If we select a target phase margin of 70 degree, then the compensator will need to provide 12.3 dB gain and have a phase of 166.4 degree, providing a phase lead of 76.4 degree. We will see in next slide what is the difference between these two terms. For these requirements, a type 2 compensator can be used since its phase can be up to 180 degree and it can provide a phase lead of up to 90 degree. It is, however, important not to confuse the compensator phase with the compensator phase lead or phase boost, as we will see next. But first, let us look at the type 2 compensator transfer function. It is formed by an origin pole, a zero, and a pole, and it has the following form showing the midband gain, GM. This form is useful because if the zero frequency is placed at a low, if the zero is placed at a lower frequency than the pole, then a plateau is created in the magnitude curve, and the magnitude of the compensator right at the center of this plateau corresponds to the midband gain GM. The frequency at which at the center of the plateau is the geometric means of the zero and the pole, and we will call this frequency Fg, which is calculated with the expression shown here. Note how right at the center of the plateau at the frequency Fg, the compensator also has the maximum phase and provides the maximum phase lead. And here we can see the difference between the two terms. The phase lead is simply the phase of the compensator minus 90 degree, which is the constant phase that this compensator provides. The zero and the pole frequencies can be calculated with these two expressions in order to provide the required compensator phase lead at the target crossover frequency in order to achieve the phase margin specification. And that is if we select Fg as our target crossover frequency that we set before of 10 kHz. This approach of setting the midband gain as well as the zero and the pole frequencies of the compensator is known as the K factor. And if interested, you can consult here the original paper on the topic for more details about it. Let us see now how to implement a type 2 compensator circuit for our converter. Here we see a typical implementation of a type 2 compensator with a TL431 voltage reference device and a WL OCPT optocoupler. We can see the resistor divider R1 and R low, which for DC, they set the output voltage. And we see that the divider node is connected to the reference terminal of the TL431. But what is inside the TL431? Well, in simple terms, there is an amplifier driving an NPN bipolar transistor. Note that the transistor operates in the active region, so its collector current and its collector emitter voltage, they are related as shown here. If the collector current increases due to a sudden increase in the converter output voltage, then the collector emitter voltage will decrease and vice versa. So if the cathode voltage of the TL431, which corresponds to the collector emitter voltage of the TL431 output transistor, is taken as the output, then we can see the TL431 acting as an error amplifier, and the cathode voltage of the device will control the LED current through the LED optocoupler, based on the converter output voltage, of course. We also see an AC decoupling network, which is formed by a standard Zener dropper supply. This is used to prevent that the LED current is also modulated by AC variations in the output voltage. The Zener supply then can be seen as a low-pass filter with a very low cutoff frequency. But for the best AC decoupling, the Zener diode must be properly DC biased in order to reduce its dynamic resistance. Also, another thing to mention here is that the output voltage of the compensator corresponds to the collector emitter voltage of the optocoupler phototransistor, as it is configured in common emitter in this case. Let us see now how the compensator circuit operates in closed loop and how the control loop reacts to regulate the output voltage in our current mode flyback converter. The results used here were taken with a simulation in LTSpice, and the signals probed were the transformer, primary current, magnetizing current in gray, the voltage across the sense resistor after ramp compensation applied in gold brown, the compensator output voltage in pink, and this is after being scaled down by this resistor divider RD1 and RD2, which are internal to the controller which we used, the NCP12700. Then we have the optocoupler LED current in black and the cathode voltage of the TL431 in green, the converter output voltage in blue, and the converter output current is shown in red. Let us consider the event of a sudden reduction in the load current of the converter, as we see here. So the output voltage will immediately increase since now more energy is being transferred to the output than it's needed. That will cause the cathode voltage of the TL431 to decrease, and together with that will cause the LED current to increase since now there is more voltage being applied across the LED resistor and the optocoupler LED. Higher LED current will cause a higher collector current of the optocoupler phototransistor because they are just related by the CTR of the optocoupler, a gain term. So we have higher collector current flowing across the collector resistor RC. That will cause higher voltage drop across this resistor, which in turn will result in a lower collector emitter voltage, since VDD is fixed, is a DC voltage in this case. And we can see how, as we mentioned in the previous slide, the collector emitter voltage corresponds to the compensator output voltage, and we see how it effectively decreases, and at the input of the comparator, it sets a lower peak current limit in the converter, and we can see how the transformer magnetizing current, the primary current, also reduces, and the output voltage then can go back to its regulated value, because now less energy is being stored and transferred to the secondary side, its switching cycle. Note that the same will happen, but the other way around, if there is a sudden increase in the load current of the converter, as we see here. But for the compensator circuit to operate as shown before, the TL431 and the optocoupler need to be properly DC biased. In particular, both transistors must operate in their active region in steady state conditions. Starting with the TL431, it requires a minimum cathode current of around 1 milliamp and a minimum cathode voltage equal to its internal reference voltage. This can be 2.5 volt or lower depending on the device, but for the device considered here, the AS431 from Diocinc, that is 2.5 volt. In order to ensure a minimum supply current to the TL431, a resistor RB can be connected across the optocoupler LED. It takes advantage of the LED voltage drop to create a mostly constant supply, since in normal operation, there is always current flowing through the optocoupler LED. The minimum LED forward voltage of the WL or CPT optocoupler, and we see here the curve from the datasheet of around 0.85 volt, then is considered. And if we select a 430 ohm resistor for RB, we ensure a minimum bias current to the TL431 of 2 milliamp. Regarding the minimum TL431 cathode voltage, this is determined by the center voltage, Vz, minus the maximum LED forward voltage drop, which we can take from the curve of the datasheet depending on our operation temperature, and minus the maximum voltage drop across the LED resistor. So the center voltage is set in this case to 9.1 volt, and we will see that later. Then the maximum voltage drop across the optocoupler LED is also known, and what we need to find out now is what is the maximum voltage drop across the LED resistor. Well, the maximum voltage drop across the LED resistor will happen, obviously, at the maximum LED current. And the maximum LED current will happen at the maximum collector current and the minimum CTR of the optocoupler. The maximum collector current will happen when the collector emitter voltage is close to zero. In this case, it will be at the saturation level of the WLO-CPT optocoupler. Doing some circuit analysis, we will get to this expression for the maximum LED resistance to ensure that the cathode voltage of the TL431 stays above 2.5 volt. All values here in this expression are known with the exception of the minimum CTR of the optocoupler. Let us see now how we can estimate the CTR range to consider in this design. As it is already known, the current transfer ratio or current gain of the optocoupler has a wide tolerance due to technology, process, and material limitations. For this reason, optocouplers within a series are typically classified in binnings depending on the measured CTR value at a determined DC bias condition. For the case of the WL OCPT series, this is 5-volt collector emitter voltage and 5 milliamp LED current. And here we can see examples for the 4 different binnings. For example, for the bin A, the CTR will be between 0.8 and 1.6 for this DC bias condition. This is another way to express the CTR in percentage. It is, however, important to mention that the CTR also changes with LED current and with operating temperature. That means that for a different DC bias condition, the CTR range will also be different. And here in the image, we can see the dependency of the CTR, absolute CTR, versus LED current for the 4 different binnings of the WL OCPT 817 optocoupler series. This curve can be used as a reference for a rough estimate of the CTR value. However, they are only measured for a specific device within each binning, and that means that they will also change from device to device. Being now aware of the CTR variations and dependencies, in order to find the effective CTR in this design, we need to know the DC operating point of the optocoupler. In closed loop operation, the collector emitter voltage of the phototransistor, which is the compensator voltage, is set by the control loop action to generate a specific duty cycle depending on the converter operating conditions, like input voltage or output current. This voltage can be obtained with a SPICE simulation, as we show in previous slide 9. And after the presentation, when you get the slides, you will see how the voltage in the compensator corresponds to the calculated voltage from this analytical expression. As said, this is a formula also to calculate it analytically, and this is valid for a peak current mode flyback converter in continuous conduction mode operation. Both analytical and simulation results give a collector emitter voltage of 2.7 volt. A bit of clarification about the terms of this formula. This KDIV term, which is 6, this is simply the ratio of the resistive divider RD1 and RD2, which we show in the previous slide, which is inside of the NCP 12700. In this case, is 6. We take a compensation ramp at the middle of the range of 55 kilovolt per second. RS is the current sense resistor, which in this case is 0.15 ohm. LP is the magnetizing inductance of the transformer, in this case 41 microhenry, and the max is the maximum duty cycle for minimum input voltage is 0.49. With this voltage, we have a phototransistor collector current of 0.46 milliamp. And with this information, we can now measure the CTR directly by using the setup which is shown here. The voltage source, VDD, and the optocoupler output resistor, they are already set internally by the NCP 12700 controller at 5 volt and 5 kilo ohm. The LED resistor is selected here of the same value for convenience, and we will see in a moment why we do that. Then we just need to increase the DC supply on the LED side until the collector emitter voltage reaches 2.7 volt. At this operating point, the ratio of the voltage V2 to the voltage V1 will directly give the CTR value. However, this is only true if both resistors are set to the same value as it was done here. So we measure 20 samples from the WL OCPT from the bin A, and we find a CTR between 0.59 and 0.71. If you like spice simulation, you can also obtain the CTR value by using the spice models of the WL OCPT series. Each binning within the series has its own spice model with a CTR which is set close to the average value of its corresponding bin range. The simulation circuit uses a simple closed loop to set the collector emitter voltage of the phototransistor, and it uses an error amplifier, again with a voltage control voltage source, and the error signal is simply being injected as the LED current by this arbitrary current source here. And then simply by the ratio between the collector current to the LED current, we can obtain the CTR at this DC bias point. In this case, we set it at 2.7 volt as calculated before, and we obtain a CTR of 0.71. So we take a nominal CTR value of 0.71, but the production tolerance of the bin A also need to be factored in, which in this case is plus minus 30%. This gives a CTR range between 0.49 and 0.91. Now considering the temperature influence, for a temperature range between minus 40 degrees and plus 85 degrees, we see how we need to calculate the minimum CTR by a factor of 0.85. The maximum is 1, so it does not change here. These curves are provided also in the WLOCPT Optocoupler datasheet. Finally, the degradation over time for the operating conditions in this design need to be considered, but in this case, it's practically negligible after calculations based on the application node lifetime of optocouplers ANO006 from Burst Electronic, which was used in this case. Here we will use a CTR rounded down to 0.4 or 0.35 in order to provide some additional margin. Knowing the minimum CTR, we can now calculate the maximum value of the LED resistor, which is around 1.1 kilo ohm. A 1 kilo ohm resistor will be selected here, and the next step is to select a sender voltage, but we did it before, as we show, and we select in this case 75% to 80% of the output voltage. However, here a few trade-offs need to be made between AC decoupling and the effective dynamic range, which is left to the TL431 to control the LED current. Knowing the sender voltage, then in order to ensure a minimum DC bias current to the sender diode of 2 milliamps, we calculate the maximum sender resistor, and we select a 470 ohm part in this case. We see that the power dissipation both in the sender resistor and in the sender diode are acceptably low. And finally, the divider resistor values are calculated to set the output voltage to 12 volt. We set the output resistor to 10 kilo ohm, and then the output resistor calculates to be around 38 kilo ohm. The DC bias design is now completed, and we can move on now to design the compensator with the components which are still waiting to be calculated. And these are C1, R2, and the external collector emitter capacitance C-core. For the compensator design, we need the equivalent AC circuit model from the output of the converter to the output of the compensator circuit. The TL431 here is replaced by an error amplifier, with the output being taken as the cathode voltage of the device. We also see this resistor RD. This is simply the dynamic resistance of the optocoupler LED. It should be much lower than RB, but it is included here for completeness. The equivalent AC circuit of the optocoupler is highlighted here in blue. It is modeled as an isolated current gain stage as a current source dependent on the LED current and the device CTR. We also see a parasitic capacitance C-opto at the output of the optocoupler. Analyzing the circuit, we come to the expression shown here for the transfer function of the compensator between VCO and Vout. We observe that it has the structure and the characteristic of a type 2 compensator, which we already introduced before for convenience. We have a mid-band gain, GM, which in this case will be set by the resistor R2, since all the other component values, which also set the mid-band gain, were already calculated for the DC bias design. Then we have a 0, which is set by the capacitor C1 and the resistor R2. In this case, since R2 is already used to set the mid-band gain, the 0 frequency will be set by C1. And then we have a pole, which is set by the collector resistor RC, together with the total capacitance across collector emitter of the optocoupler phototransistor, to which the optocoupler parasitic capacitance is also included. So now we can calculate the component values. The requirements for our compensator were already set before and are again recalled here. Applying the K-factor method, the required zero and pole frequencies for a phase lead of 76.4 degrees are 1.2 kHz and 83.25 kHz respectively. A value of 44.2 kilo ohm for R2 will set the required mid-band gain. In order to set the zero frequency at 1.2 kHz, a capacitance C1 of 3 nanofarad is required. We will select a standard value of 3.3 nanofarad. The required compensator output capacitance to set the pole at 83.25 kHz is 0.38 nanofarad. So if the collector emitter parasitic capacitance of the optocoupler is higher than 0.38 nanofarad, it seems that the pole cannot be set at the target frequency. But what is the optocoupler capacitance and its associated pole frequency in this case? Let's see. There are different ways to find the optocoupler collector emitter capacitance. In this case, we will measure the device frequency response. For that, we use a vector network analyzer like the Bode 100 with the signal injected with the BWIT 100 injection transformer. The output is taken across the two resistors. The procedure for setting the optocoupler DC bias point for the measurement is exactly the same like for the CTR measurement, which we saw before, and with the proper DC bias, the same 20 samples of the WL OCPT 817 optocoupler series from the bin A were measured, and here is the result for one of them, specifically the one with a CTR of 0.71. We see the cutoff frequency, where the magnitude drops to -3 dB as usual, to be 24.5 kilohertz. If we consider the 20 samples, we get an average cutoff frequency of the optocoupler of 24 kilohertz. That corresponds to a parasitic capacitance between collector emitter of 1.3 nanofarad. This is higher than 0.38 nanofarad. So what can we do about this? Let us see some possible solutions to this. The first solution which might come to our mind is simply to select a lower crossover frequency, so that a lower compensator pole frequency is required, staying within the range that the optocoupler can do. So we try with 3 kHz. We check the magnitude and the phase of the control to output transfer function at 3 kHz in order to get the new compensator requirements. And this is minus 2.1 dB and minus 82.4 degree. The compensator then needs to provide a midband gain of 2.1 dB and a phase of 152 degree with a phase lead of 62 degree at 3 kHz. We calculate the required zero and pole frequencies for this new specification following the K-factor approach shown before, and this gives 750 Hz for the zero frequency and 12 kHz for the pole frequency. We recalculate R2 to set the midband gain and C1 to set the zero frequency, selecting close standard values available. In order to set the pole of the compensator at 12 kHz, we see that a total collector emitter capacitance of 2.6 nanofarad is required. Since the optocoupler capacitance is 1.3 nanofarad, as we measured before, then adding another 1.3 nanofarad will do. We select a standard 1 nanofarad capacitor. This will result in a slightly higher pole frequency of 13.8 kHz. And here we see the results of this compensator design. At 3 kHz, 2.3 dB, and 153.6 degree phase are provided. We see that the results are very close, but not exactly equal as the specification. And this is because we use the standard values for the components instead of the exact calculated ones. Another possible solution, which will allow to keep a higher crossover frequency of 10 kHz, as initially was selected, is simply to add a zero and a pole to the compensator. The zero will cancel the optocoupler pole, and the new pole will be set at the required 83 kHz. The pole and the zero are implemented by simply adding a resistor R3 and a capacitor C3 across R1, as it is shown here in the schematic. We can see that this, in reality, corresponds to a type 3 compensator configuration with an origin pole, 2 zeros, and 2 poles. However, since 1 zero and 1 pole will cancel each other, we will have the typical type 2 compensator response. Since the optocoupler pole will be cancelled by the zero, additional capacitance can be added at the compensator output. This has the advantage of reducing the effect of the optocoupler pole frequency variations, which are dependent on the optocoupler CTR and the collector emitter voltage. If we add a 3.3 nanofarad capacitor, the new pole frequency is 6.92 kHz. The resistor R3 is calculated to place the zero at this frequency. And then the capacitor C3 is calculated to set the compensator pole at 83.25 kHz. So selecting, again, standard values, we have here the results where we can confirm how it is really a type 2 compensator response. And also the values are close but not exact to the target specification of 12.3 dB and 166.4 degree. And as before, this is due to selecting standard value components. Let us see now the resulting open loop response and transient behavior of the system for both compensator design solutions. Here we can see the Bode plot of the open loop transfer function for the first design solution. A crossover frequency of 3 kHz with a phase margin of 71.1 degree and a gain margin of almost 25 dB is observed here. And here we see the results for the second design solution. We see a crossover frequency of 9.2 kHz with a 69.2 degree phase margin and almost 15 dB gain margin. Both designs are stable and with good phase and gain margins at the operating conditions considered, which is minimum input voltage and full load current. And here we have the transient response for the two compensator design solutions. This was obtained with LT-Spice and also using an average PWM switch model, and that is the reason why we don't see any switching ripple noise on the waveforms. In both cases, we can observe how it is a well-behaved response without any ringing, just thanks to the high phase margin. However, it can be seen how the higher crossover frequency of the second design solution, here in red, allows for a faster control loop reaction to the transient, which in turn results in lower overshoot and undershoot, and also to a faster settling time. This is because a higher open loop crossover frequency leads to a higher bandwidth of the closed loop system. Let us see now what can happen as the CTR and the parasitic capacitance of the optocoupler varies. As we have seen, the compensator midband gain is directly proportional to the CTR value of the optocoupler, so as the CTR varies, the midband gain will also change. This can be seen here in the Bode plots, how the CTR variation shifts the magnitude curve of the compensator up or down in our design. Knowing this, we can advance that the open loop crossover frequency will also change, and with it, the phase margin affecting the transient response. One thing to note, and which is not reflected in the curve, is that if the CTR changes, the optocoupler pole frequency will also change since they are interrelated. And this will also affect the phase curve of the compensator and in turn the phase margin. And here we can see the effect of the midband gain variations on the crossover frequency and phase margin of the system. A crossover frequency variation between 1.7 kHz and 3.7 kHz is observed, with the phase margin varying between 75.1 degree and 66.5 degree. In this particular design, since the phase curve shows a very soft parabolic roll-off, the phase margin does not change that much. We have the disadvantage, but we need to check it. It is also important to know that the optocoupler pole frequency varies with optocoupler CTR, which then also changes with LED current, which in turn depends on the collector emitter voltage in this application. The collector emitter voltage, as we saw, is the output voltage of the compensator, which is set by the control loop action based on the converter operating conditions like input voltage and load current. Here we can see the results for 10 samples of the bin A of the WL-OCPT817 optocoupler series, and the measured pole frequency for different collector emitter voltages is shown. This represents different operating conditions of the converter. it can be seen how the optocoupler pole frequency for each sample reduces with the collector emitter voltage. This means that for a set input voltage, if the load current reduces, then the optocoupler pole frequency will also reduce. Conversely, for a fixed load current, the optocoupler pole frequency will increase as the input voltage reduces. However, some parameters in the plant transfer function will also change with operating condition, like the DC gain, the dominant pole frequency, and the right half plane zero frequency. For this reason, it is very important to check stability for all operating conditions and taking into account all these variations. For such assessment, spice simulation with average models is very useful. Let us see now finally some experimental results. A prototype has been designed and built with the specifications already shown before and shown here again for reference. And here is an image of the prototype board. We start by measuring the plant or control to output frequency response. It was used again, the bode 100, with its injection transformer BWIT 100 for the measurement. We also used a 4.7 ohm load resistor, which will be drawing around 2.55 amp. And we have here the result for full load and minimum input voltage, 36 volt. At both target crossover frequencies of 3 kHz and 10 kHz, experimental and analytical results match very well. We have a discrepancy of 2.5 degrees in phase at 3 kHz and also at 10 kHz, where we measure a slightly lower gain of 12.1 dB instead of 12.3 dB. We also see how the resonant double pole peaking in the magnitude is also well damped. And here we can see the experimental results for the first compensator design. With a target crossover frequency of 3 kHz, the compensator had to provide 2.3 dB with a phase of 154 degrees. Experimental results show 2.6 dB and almost 156 degrees in phase. This is a good approximation, but not exact due to several factors which were not considered. Regarding the difference in gain, we have the bias resistor RB for the TL431, which is in parallel with the optocoupler LED. And it diverts some current from this, since the dynamic resistance of the LED is not exactly zero. And that reduces the compensator gain. The same happens as the AC decoupling of the Zener network is not ideal. In addition, in the design, the static CTR of the optocoupler was considered, whereas the dynamic CTR is a bit higher, increasing the gain, and this seems to be the dominant factor here for a slightly higher gain. The measured open loop response shows a crossover frequency of 3.2 kHz and a phase margin of 75 degrees with a gain margin of 19.6 dB. Example of possible adjustments could be to reduce the capacitor C1 in order to increase the compensator zero frequency, and with that, we can bring the phase margin down to 70 degrees. And here we see the experimental results for the second compensator solution. With a target crossover frequency of 10 kHz, the compensator had to provide 11.6 dB with a phase of 165 degrees. Experimental results show 12.5 dB and around 159 degrees in phase. The reason for the higher gain seems to be mostly due to the higher dynamic CTR, as in the previous case. However, regarding the phase, it is lower than expected, and looking into more detail to the experimental measurement, we can see how the magnitude roll off after the compensator pole at around minus 60 dB per decade, instead of minus 20 dB per decade, which is what we would expect. And the phase, we also see that it approaches minus 90 degree instead of stabilizing at plus 90 degree. This hints to two further poles which are present around 100 kilohertz, which already have some effect at the target crossover frequency of 10 kilohertz, reducing with it the phase. These poles were not included in our analysis since they are at higher frequency, but however, if necessary, any adjustments can be performed now with experimental results. The measured open loop response shows a crossover frequency of 10.4 kilohertz and a phase margin of 59 degree with a gain margin of 10.2 dB. Although the design is stable, example of possible adjustments could be to increase the resistor R3 in order to lower the zero frequency, as well as to reduce the capacitor C3 in order to move the compensator pole frequency higher, and with that, we can increase the phase margin to 70 degree as the target. These results were taken with a WLOCPT optocoupler device with a CTR of 0.71 at the DC bias conditions. However, we know that the maximum CTR will be 0.9, as we calculated before. So what is the optocoupler pole frequency with a device with a CTR of 0.9? Well, we measure it and find a cutoff frequency of around 18 kilohertz. Since the phase curve of the open loop response rolls off continuously, this combination of highest CTR causing the highest midband gain of the compensator, together with lowest pole frequency, will result in the highest crossover frequency and the lowest phase margin in the case of this design. And this can be taken in this case as the worst case. Let us see the results now for the two compensator design solutions at the maximum expected CTR of 0.9. For the first design option, the crossover frequency is higher as expected, in this case 4.2 kilohertz, and the phase margin reduces to around 68 degree, while keeping a high gain margin of 17 dB. For the second compensator design, the crossover frequency is 13 kilohertz and the phase margin around 49 degree, still above 45 degree, which was our worst case minimum considered in the design. The gain margin is 7.6 dB, still well over the minimum recommended of 6 dB. So we can see that at the maximum CTR of 0.9, both compensator designs are still stable, but with a reduction in the phase and gain margins as we advanced in previous slides. However, and I repeat here, full stability needs to be confirmed by checking for all other operating conditions. You should not give it for granted. And here we see the transient response to a low current step from 2 amp to 2.5 amp at a slew rate of around 1 amp per microsecond. Both scope captures have the same scale for an easier comparison. And the results correspond very well with those from simulation, which were shown in a previous slide. We see how both compensator designs are stable. However, the second compensator design with a higher crossover frequency of around 10 kilohertz and a lower phase margin provides a faster settling time with lower overshoot and undershoot.
Attached images and videos are available in most podcast streaming networks. You can find the entire line of Worth Electronic optocouplers available at Worth Electronic online. This podcast was taken from an updated Worth Electronic webinar. To view the materials and replay the webinar on demand, visit our website at www.we-online.com/webinars or click the link attached in this podcast. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic tech specialists who are going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.